Hello everyone. In today's lesson, we're going to talk about our first video for physics, which is the very difficult concept. Okay, so many students has feedback to me, wow, sure, this one's very difficult. So that's why I feel that I should record a video to better explain this again, so that those who are with me for tuition can watch again. Those who are not yet with me yet, you can watch it once, and then you probably should have a much better understanding of this topic after the video. So this topic, known as the electromagnetic induction, in terms of arrangement wise, is actually one of the last topic, used to be last topic before radioactivity was reintroduced in the O-level syllabus. So, and this is an extremely important topic for engineers, because this is actually where I would say electrical energy is converted, or in today's context, maybe you will know it as electrical energy transferred to the electrical store in some cases. So you can talk about it in terms of store as well, but using the old way of looking at this is talking about electrical energy converted. Yeah, we do not say that it's producing, although they are called generator, but however, this energy is in fact converted from other forms. Okay, if you look at the pictures over here, these are the things that we commonly use to generate this electrical energy that we want, or converted, right? So the very first one, this is called the wind turbine. So wind turbine is when wind blows, the turbine will be spinning, and the spinning action will then help you to generate the electrical energy that you want. Okay, once again, converted. Okay, next we have the water turbine. So water turbine, this is the end point at the bottom. By right, the start point should be at the top where you have a reservoir. So when the waters are being collected, there will be a dam to actually trap the water. And when they open the dam, the water will run down, and then it will cause this turbine to spin. All right, so thereby generating electrical energy. And of course, the last one over here. So this is a water turbine. The last one is called steam turbine. So steam turbine is, as the name implies, they use steam to drive the turbine, and thereby creating the energy that you want. Okay, generating the energy that you want. But really, this is the commonly done thing that we have been doing so far, but we are trying to move away for other source of energy, because steam turbine is not so preferred in today's context as a result of the frequent use of fossil fuel, and that will cause a lot of global warming. Okay, but right now, this is traditionally what we have been producing energy from, so this is still currently being used. So steam turbine. Of course, moving on, there's also various other methods to generate the steam that we want, so but that's for another video. Alright, but at the end of the day, all these things that we see here, they generate the electricity that you want, and this is the reason why we can enjoy the laptop, the power bank, and also the lights all around you. Right? It's all thanks to these generators. They are working very hard to generate all this electricity for us. But of course, the question is the how part. A lot of times when you first learn about electrical energy, you will know that there's this thing called a generator, but often the part of how it actually happened has been left out. The main reason is because that there are more things that you need to learn before you can understand, fully comprehend exactly how the process works. Okay, so all this started from a very simple experiment called the Faraday's experiment. So in the Faraday's experiment, what happened was a magnet will be pushed towards this coil. Okay, this coil is a conductor, and this conductor is also commonly known as a solenoid. Okay, so when you push a magnet close to the solenoid, at the bottom part, you will have this thing called the galvanometer. This galvanometer will help you to detect current. So whenever electric current flow, the galvanometer will be jumping to tell you that yes, there's an electric current flow. So surprisingly, it's not to detect the thing that you're creating out of this scenario directly, but really the current flow. Okay, and of course, when the magnet moves towards the coil, then there will be a deflection. And from the deflection, we suggest that there must be a presence of electric current. So energy is actually present, which can only be explained by the movement of the magnet. As you can see in this setup, there was nothing, no battery at all. So if the question is talking about induction in the exam, please remember to look out for whether in the circuit has any EMF. So no EMF source, and yet the question is talking about the light bulb lighting up, then definitely this will translate to it's an induction question. You can use that to help you to remember what you're looking at, because after learning the previous topic called electromagnetism, you know that any electric current will produce magnetic field and so on. So you might be a bit confused. Then you got various hand rule that you learn, and right here there's also another hand rule. However, the thing is that it's quite confusing. Are we looking at induction, or are we looking at electromagnetism only? Is it just the force part? Yeah, so it can get a bit confusing. So please use this fact to help you to remember. If let's say the circuit does not possess any EMF, so meaning to say they don't have battery, they don't have cell, then it should be induction, right? Yet there will be current flowing through. Okay, then coming to the next part. Actually, this topic, as I always share with my students, it is quite short because there's only 2 rules that you need to learn. But these 2 rules has many different applications, which is very confusing. So the first rule, or this is first law. It's not a rule, that is the Faraday's law. So under the Faraday's law, it is to talk about the amount of electrical energy that you can create, okay, or what we call the induced EMF in this case. So the potential difference, the EMF that you can create, the battery that you can create, is really dependent on the rate of change of the magnetic flux or magnetic field. So take note, the thing that you want to highlight here is the change. If there is a magnetic flux cutting a conductor, but it is constant and do not change, then we don't say that there's induction. Induction only happens when you put the magnet in front, okay? Right? Let's say you have a magnet, right? North pole, south pole, then there's a coil. So, and probably there's a galvanometer. So let's say if you just put the magnet in front, then you say that, oh, in this case there's induction because there's magnetic field cutting the coil. Okay, so answer is no. Okay, it does not. Because only when you decide to move the magnet back or move the magnet forward, then an induction will happen. Because the movement of backward and forward will cause a change in the magnetic field. And according to the Faraday's law, something will happen at the solenoid coil. There will be induced EMF. Okay, so a more layman way of looking at it, I think this might be easier for you to understand. Faster the magnetic field change, the stronger the battery produced. Because according to the question, according to the text, directly proportionate. So if you go faster, it's a rate. If you go faster, there will be a greater rate of change, and then that result in more EMF induced. Okay, so Faraday only talk about the how much is the induction. Okay, that's all. How much? You cause a greater rate of change, use a stronger magnet, you move faster. All these are things that will cause a greater rate of change. But that is according to the Faraday's law. And it does not really talk about anything else apart from the how much is being produced. Okay, so if you are looking to explain the how much has been produced, please use the Faraday's law. Okay, an example of the Faraday's law might be this. So imagine that you have a lamp. This lamp is connected to a dynamo. Okay, this is called a bicycle dynamo. So inside a bicycle dynamo, there will be a coil, which is a conductor. So this is the conductor, right? Whenever we talk about induction, there should be a conductor, and there should be a changing magnetic field, which is due to the rotating magnet. So when the magnet rotates, it will be cutting the coil over here, which will thereby causes induction. Now, if I link 2 wires, okay, from this conductor, you can see, right? Then this is linked to the lamp. We expect as you cycle, the energy from you when you cycle, the kinetic energy will be then converted to this electrical energy to power the lamp. Yeah, so this is one of the applications of Faraday's law. Why would the lamp turn up? Because there's induction. Okay, the energy is being converted from kinetic from you to electrical, and eventually it will power up the lamp to light energy and so on. Yeah, so this is one example of the Faraday's law. Okay, next, Lenz's law. Lenz's law, on the other hand, talks about the the way that the EMF is being created and what do you get out of it. So it's mainly talking about direction here. But apart from that, the main thing that we use Lenz law to explain, right, is talking about how come the things that I'm doing will be opposed. So the keyword here is opposing magnetic field. Right. So for example, if I once again have a solenoid coil, I put a magnet of north pole, south pole. If I were to push it in, you will find that it is not as easy to do so. So once again, there's a galvanometer here. When you push in, you'll find that the galvanometer needle will actually deflect, let's say, to the right. Okay, when you push in. So next, if let's say I were to pull out, let me use blue color to represent pull out. If I were to pull out, so north pole again, right, I find that the needle will deflect in the opposite direction. Okay, so this can only be explained by the Lenz law. So if you're talking about how come there's a deflection, then I would say it's Faraday's law. But how come the direction changed, right? It's actually Lenz law, because the thing that you did, the change was different. So when you push the magnet in, you are increasing the magnetic flux. So it's a change, but it's an increase. But next, if you were to push it out, then that will cause, okay, so this is for this. Then if you were to push it out, then you are decreasing the magnetic flux. So as a result of that, you will find that the things that you are doing is different. And the way that the system here, the solenoid coil, wants to react by inducing the EMF and current is actually in such a way to oppose the way that you do it. So the reaction itself will be always opposite. And of course, when you are pushing the magnet in, then the thing that you will experience will be, okay, let me draw in black color. You will experience a force in this direction. So to push you away. So the opposing effect has got to do with that. Then if you are trying to pull it away, then the force will be in this direction. So to pull you back. So it's always opposite. There are of course a lot more examples to this Lenz law, but I think the basic idea of opposing effect is what I want to tell you at this point. So imagine if let's say you are trying to explain how come there's opposing effect, then please remember to quote Lenz law. Okay, Lenz law will be able to help you to explain that, because of the fact that there will be an effect of opposing magnetic field created. But coming to the point of the magnetic field, it is also important to remember that this opposing magnetic field only happens if there is a presence of a, okay, it's over here, sorry, induced current. So when there's induced current, then this opposing effect will happen, which also means to say that this is uniquely for a closed circuit. If the conductor that you are using is not a closed circuit, it doesn't form a closed circuit with anything else. So just now, as you can see the solenoid, I added the galvanometer because I want to explain the Lenz law. I need to make sure it's a closed circuit first, so that there will be induced current producing the field to oppose the effect. Okay, so remember that you need to have a closed circuit. It is always the case where we have an induced EMF, but not always the case where we have an induced current, because that depends on whether the circuit is closed. Okay, example of the case of using the Lenz law will be in terms of eddy current breaking. So it's very common that when we talk about machinery, car, or even some cases, that whenever the wheels rotate, there will be a disc that's attached to the axle. Then this will be rotating within the magnet, the electromagnet. So which means to say that if the magnet is on, the electromagnet is on, you will be cutting the field and then thereby creating a force that's opposing the motion of the rotation. So let's say in this case, you were talking about this thing is trying to rotate in this direction. Because of Lenz law or induction, you find that there will be current induced here that produce a magnetic field opposite to what you're trying to do. So in this case, if you are trying to rotate anti-clockwise, then you will find that you will not be able to do that so well, because there will be a force to go against it in the opposite direction. So step will be, there will be EMF induced. Closed circuit, you get an induced current. Current produce magnetic field. And last but not least, this magnetic field will oppose motion. So that's how I would see it. In describing the reason why the disc is being opposed, you might want to go through this step. Talk about the presence of the EMF induced because got magnetic field cutting, and then after which there's an induced current because of a closed circuit, and this induced current thereby produces a magnetic field which opposes your motion. Yeah, so I will think of it as this few step if I'm supposed to explain the effect of eddy current breaking. Okay, now we're going to close up the lesson by looking at two example questions. So you might find this question fairly familiar because this is normally the things that you will be asked in the exam as well. So the first one is pertaining to the Faraday's law. In the following setup, the light bulb is connected to a bare wire. So we're talking about this one. This is a bare wire. Okay, and there's also a solenoid here, okay? And at the end with no battery connected, no battery connected. So using the laws of electromagnetic induction, explain why when the magnet rotates, the light bulb will light up. Okay, so in this diagram. So by right, we don't expect the light bulb to light up since there's no EMF source, no battery. But when you rotate the magnet, magically it happens. Okay, so the question is asking you why. So important for you to point out where is experiencing the changing magnetic field. So in your answer, you should be talking about that first. So point number one, as the magnet rotates, the solenoid experiences a change in magnetic flux, the field lines, okay, which is I'm talking about this part. So then moving on to the next part, according to the Faraday's law, if that's the case, then there should be EMF induced across the solenoid. Correct? So that's part number two. So must quote the Faraday's law. And of course, because this is a closed circuit, there will be induced current flowing through the light, causing it to light up. So this is the last part. So of course, you need to talk about closed circuit because the presence of electric current is what that power up the light bulb. If let's say it's not a closed circuit, I don't think we will expect to get that. So that's the thing to remember. Okay, so very systematically, you talk about a description first. So always start by describing what happened. It's important in EMI. Then after which, right, you quote the law that's applicable. If you want to talk about why is there electric current, then there will be the Faraday's law because there will be induced EMF. Last but not least, you want to explain why eventually the light bulb will light up because this is a closed circuit. Imagine if I were to have a switch or make a cut in the wire, then the current cannot flow to the light bulb. And in this case, we don't expect the light bulb to light up. Okay, so three parts. A typical question like this usually will be worth 2 to about 3 marks. In some cases, they can even up to 4 marks or 5 marks, depending on the number of things they want you to explain. But this part is really talking about why the light bulb light up. So I think this is good enough. Faraday's law will be good enough. Okay, so the next question that we're going to look at will be talking about the Lenz's law. So eddy current breaking, once again, you can see that in this case, it's talking about zip lining. The person is trying to move down, and there is a system attached to the top. So within this system, actually, you will have a setup like that. That's the entire point of this question. Okay, so they gave you all this information. And because when you pull down, the string will be causing the wheel to spin. And this spinning will actually cause this disc itself. It will be spinning within the magnetic field, and then thereby causing some breaking effect. But take note that it won't make sense if let's say the magnet is constantly on. Otherwise, the person will not be able to go down because there's always breaking effect. So what will happen is that, right, usually this part is highly likely that it's going to be electromagnetic. So which means to say that, right, I will be turning it on when I need it. Yeah, so I will not turn it on always. If I want the person to go down, I will probably not turn it on. But as we reach the bottom, closer to the bottom, then you need to turn on the system in order to make sure that the person is being slowed down, okay, not hitting the ground. That's very dangerous. Okay, so we are supposed to explain why is there this breaking effect. Okay, so if you remember just now, we still need to go through it, but a bit different from the previous question is that we don't just stop at talking about the production of the current, but really we want to talk about what this current do to talk about the opposing effect. So if you look at the answer, point number one, as the person descends, okay, so you see, I start by describing what happened. He will cause the disc to rotate, and then the disc will cause the magnetic field to be cutting, okay, through the magnet. There's a magnet, so it will be cutting through the magnetic field of the magnet. And once again, back to the Faraday's law, there will be an EMF induced. Okay, so, but that's not all, because we want to lead to talking about why is there a force. So the second part will be, because of that, there will be induced current in the disc, because the disc itself is a electrical conductor. And more importantly is that there is enough space for the current to flow. So I can create two regions where there's higher and lower potential. So there's a PD, right? Then the current can flow. So there must be enough space as well. So there will be electric current and the current can flow. And this current will produce a magnetic field that's opposite. So it's important to point this out, that according to Lenz's law, will produce a force opposite to the turning of the rotor in order to cause the thing to break. Okay, so this is the last point. In fact, a lot of amusement system, namely your roller coaster, or possibly your, if you played those drop tower before, where you want to fall from a certain height. So actually there's induction going on to help you to break the system. So when it's moving very fast, there's a lot of induction, then there will be a lot of opposing force to help you to slow down, and the braking force can be adjusted according to the speed of the amusement ride itself, up and down. So this is really a very amazing introduction to that. Yeah. Okay, so with that, I think I've come to the end of this video. Okay, if you like my physics video, please look forward to the next one, which I'll be filming. And you can also try to watch some of my mathematics and chemistry videos as well if you find them helpful. Okay, thank you very much. And if you like, please help me to subscribe to the video as well as share with your friends, so actually more people can get help. Okay, thank you very much. I will see you again in the next video.